Hello everyone and welcome to Sky Scholar. Today I wish to begin by thanking everyone for taking the time to view these videos. One never knows who is viewing a video and in turn bringing the subject to the attention of others. The sharing of information has been responsible for much of the growth of Sky Scholar. So thank you. It is important to note that I do consider the comments that are made by the viewers. If an error is made, I will correct. Otherwise, the videos stand as produced, despite the comments of some of the detractors. That being said, a few weeks ago, I produced this video on nuclear reactions in the Sun, and Michael C. brought something to my attention which was tremendously important to the condensed model of the Sun. Here is a screenshot of the comment addressed to my friend Steve Crothers. This is the important section of what Michael writes. Does this have any bearing on Robitaille's model of the Sun? And I am not a physicist and simply noticed the idea of a metal lattice facilitating a nuclear reaction. Steve Crothers did answer, as did Ian. If you are interested in the flow of the discussion, it is under a response to a comment initially made by YK Chan. I cannot thank Michael enough for bringing this paper to my attention. He noted an experiment which is extremely important to understanding fusion reactions and the energy that is required for initiation. In fact, I believe that these experiments and others like them will eventually help to clarify that the stars can make all the elements. First-generation stars are not needed. The paper describes lattice confinement in fusion reactions. The idea is that if one confines an atom to a lattice, it is possible to lower the Coulomb barrier and greatly facilitate fusion reactions. We will return to this shortly. In these two videos, I had emphasized that the Sun has convection currents and that these currents possess enough energy to facilitate nuclear reactions. In fact, the temperature equivalent of the energy in the solar convection currents might be on the order of millions of degrees. Furthermore, in the second video, I briefly touched on the fact that the astronomers do not believe that the Sun has a lattice. As a result, I mentioned that solar physicists have ignored all the advantages of the lattice in positioning nuclei for reactions and in transferring energy into a set of nuclei. Now, 10 years ago, this special issue of Progress in Physics was produced. In the summary paper, I stated, for astrophysicists, the Sun imparts lessons which may well have direct applications for mankind. For instance, the solar body holds the key to fusion. If the Sun is made from condensed matter, then our experiments should focus on this state. A few years later, I expanded on the concept. A metallic hydrogen framework can restrict protons to lattice points in the hexagonal plane and confine other atoms to the intercalate layer. Solar pressure and lattice vibrations could act in concert to enhance the probability of nuclear reactions. Two adjacent protons in the hexagonal plane could give rise to a deuterium atom with the associated positron and neutrino emission. This deuterium atom could then react with another, leading to the direct synthesis of helium-4. Alternatively, it could fuse with a proton, leading to the formation of helium-3. Both helium-4 and the light helium isotope helium-3 would be immediately ejected into the intercalate region. Over time, the intercalate region could sustain other nuclear reactions and become the birthplace of all naturally occurring heavy isotopes. The Sun and the stars gain the ability to synthesize all the elements. In the Sun, there are actually three key factors which can facilitate the synthesis of elements. The first is the lattice. The second is the energy contained within convection currents. And the third is the internal pressure. Relative to the lattice, there is another feature, namely that in metallic hydrogen, electrons are flowing in conduction bands. But before discussing the paper which Michael brought to my attention, I wanted to begin with this 2015 Russian paper as it has scientific priority. Note that this work was published in Physical Review C, perhaps the top journal in nuclear physics. In this paper, lattice confinement was utilized to achieve fusion reactions driven by bombardment with X-rays. In order to achieve this feat, the Russians took advantage of lithium deuteride crystals. This crystal has an ionic character wherein the lithium holds a partial positive charge and the deuterium a partial negative charge. Consequently, this paper mentions that the effective diameter of the deuterium atoms is about twice that of the lithium atoms. Given that lithium deuteride is an ionic crystal, there are no conduction electrons involved. Now, in their paper, the authors highlight that the atoms within the crystal are confined to their lattice points about which they oscillate. In order to have fusion, these atoms would have to possess enough energy to overcome the Coulomb barrier. You can think of the Coulomb barrier as an energy barrier. When two nuclei approach one another, they experience a strong repulsion because of their positive charges. In terms of energy, the Coulomb barrier is on the order of a few mega electron volts. That is a huge amount of energy which has a temperature equivalent on the order of more than 10 billion Kelvin. This implies that the probability of fusion of two nuclei at room temperature is practically zero, or 10 to the minus 2,600. The authors of the study remind us that the energy of atomic vibrations in a crystal is only a few milli-electron volts. But when atoms are confined by a crystal, vibrations along the internuclear distance can cause atoms to sit next to the barrier location for relatively longer times. This increases the probability of fusion. The idea in obtaining fusion in a crystal is to increase the energy involved in the atomic vibrations by bombarding the crystal with X-rays. The probability of fusion is increased by combining the effect of lattice confinement and the increased kinetic energy of vibrations due to X-ray bombardment. When this is done, a deuterium atom can acquire enough energy to overcome the Coulomb barrier and tunnel its way into the lithium nucleus, leading to the production of an excited beryllium-8, as you can see in this equation. The beryllium is highly unstable and immediately breaks down into two alpha particles traveling in opposite directions, each with an energy of 11.18 mega-electron volts. Over the course of 111 hours, a total of 88 fusion reactions were detected in this experiment. Lattice confinement was proven to help overcome the Coulomb barrier and facilitate fusion. Next, we move to NASA's work. In April 2020, NASA reported that it had achieved lattice confinement nuclear fusion as reported in these two papers, which are publicly available also as technical reports. Then, in addition, NASA presented a review of their lattice confinement in this work. All these are linked below. The idea is to start with a metal, in this case erbium. The metal is then deuterated by saturating it with deuterium atoms. This results in a packing of nuclear fuel which is 1 billion times denser than in magnetic confinement of gaseous plasma reactors. To initiate the reaction, a neutron is first produced by photodissociating some of the deuterium atoms using high-energy or 2.9 mega-electron volt gamma rays. When it dissociates, the deuterium atom breaks down into a high-energy neutron and a proton. The resulting high-energy neutron then strikes another deuterium atom and imparts upon it a tremendous increase in kinetic energy. The activated deuterium atom then has several choices. First, it can fuse with another deuterium atom. When it does, the reaction can result in the production of helium-3 and a new energetic neutron which can continue the reaction. Alternatively, when the two deuterium atoms fuse, they can make a tritium and release a proton. Of course, the activated deuterium can also interact with the erbium lattice. When it approaches the erbium nucleus, it can be stripped of its proton, which then combines with the erbium to make thulium, or it can be stripped of its neutron and make a heavier isotope of erbium. All of these fusion reactions are taking place at room temperature, but the atoms involved acquire fusion-level kinetic energies by being bombarded by neutrons. Now, interestingly, NASA examined what makes the best supporting framework for the deuterium atoms. They found that the presence of conduction bands in metals is extremely important. The presence of electrons in those bands helps to shield the nucleus and thereby lowers the Coulomb energy required for fusion to take place. Of course, this takes us back to the Sun and the hexagonal planar metallic hydrogen lattice, wherein all of the electrons are contained in conduction bands. Furthermore, remember that in the metallic hydrogen solar model, intercalate zones exist. Non-hydrogen elements reside in those zones, yet in some regions they have to be in contact with the hexagonal planar lattice. The conduction electrons might be important in this region once again to help facilitate nuclear reactions. So in closing, a condensed model of the Sun has numerous advantages in enabling the production of every natural element. There is lattice confinement of protons. There are lattice vibrations. There is also shielding effect of the conduction bands, and there is access to the kinetic energy of motion associated with convection currents. In short, the condensed sun model is so clearly superior to the gaseous model of the sun when it comes to facilitating nuclear reactions that it's hard to conceive that the gaseous model can survive much longer. Well, that is all for now. Again, thank you, Michael, for bringing the NASA paper to my attention. If you enjoyed the video today, promote the channel, mention the video to your friends and to your local astronomy club, support me with a like and subscribe for more videos as we look more closely at the sun, the stars, and beyond. Comments are always welcome down below, and I'll see you soon on our next video.